Hi everyone. Today for 14.3 we're going to start doing actual proofs where we prove that two triangles are congruent. And this is going to be our goal for the rest of Module 14. So first of all, last section we learned that corresponding parts of congruent triangles are congruent. So we said if two triangles are congruent, there are 6 different pieces of each triangle and you have pairs that are congruent. So each angle of one triangle is congruent to each angle of the other, and each side is congruent to the other. So one way to prove triangles are congruent, and this is not the way we're going to do it, but what you could do is you could take each thing, each triangle, and you could prove those 6 things. You could say, okay, first of all, step 1 of my proof, this side is congruent to that side. Step 2, this side, that side. Step 3, this side. And then all of a sudden you have 6 steps where you have to show 3 sides are congruent to 3 sides, 3 angles are congruent to 3 angles. So what we want to do is we want to have shortcuts. We don't want to have to do all 6. And that's our goal for the rest of Module 14. So we're going to have what I call the letter theorems. Theorems with a bunch of S's and A's in them. And we're going to start with SSS. And S stands for side. So what you'll see, and you'll see this on the next slide, when we do our letter theorems, every S stands for side and every A is going to stand for angle. So when we say SSS, it's actually called the side, side, side congruence theorem. But if you're putting that as a reason in a proof, instead of in that little column for reasons, instead of writing side, side, side congruence theorem, we just write SSS and we know what it means. So that's what SSS stands for, and it says if the 3 sides of one triangle are congruent to the 3 sides of another triangle, then the triangles are automatically congruent. You don't need to know anything about the angles. So in this picture right here, what you notice is you have 1 mark here and 1 mark here. That means those sides are congruent. That's basically S, one of the S's. Then you have 2 here and 2 here. That's the second S. And then you have 3 here and 3 here. So we have S, S, S. The 3 sides of one triangle are exactly the same as the 3 sides of the other. Now notice I didn't say anything about the angles. You don't have a single angle marked congruent in this picture, and that's okay. Just from that information, it's enough for me to say triangle ABC, the blue one, is congruent to triangle YXZ, the orange one. And my reason would be, if I was doing a proof, my reason would be SSS. All right, our second theorem for today is called SAS. Now I already mentioned the S's stand for sides and the A stands for angle. So when you say SAS, that's the shorthand version for saying the side, angle, side congruence theorem. And it says if 2 sides of a triangle and the angle in between them are congruent to the same pattern in another triangle, then the triangles are congruent. Now, they do have to go in order. SAS. That means like going in order around the triangle. It has to go side, then angle, then side, and it has to be the same in both. So here's an example. These 2 triangles are congruent by SAS. What you have is, here's your first S right here, side. Here's the angle right here, angle. And then here's the second side right here. So kind of going in order around the circle, it goes S, A, S, and then over here you have the same S, A, S. Now as long as you're going in order and following that pattern, side, angle, side, and it's the same in both triangles, then again, I have enough to say triangle ABC is congruent to triangle XYZ, and my reason would be SAS. I didn't need to know anything about angle A, or B, or Y, or X. I didn't need to know anything about that third side over here. I have this question mark. I don't know how long that side is. I don't know if this side is congruent to anything. Just by the SAS in order being the same in both triangles, that's enough to say the triangles are congruent. Now I want to go over one other property with you that we're going to use as a reason in some of these proofs. It's called the reflexive property, and it's kind of a weird one because it's one of those where it's so obvious, it seems like you don't even need to say it. What it says is everything is equal to itself, or congruent for shapes. If it's numbers, it's equal. It's just saying like 5 equals 5. and 10 equals 10. It's like, of course it does, it's the same number. And for a shape, it would be congruent. So like line segment AB is congruent to line segment AB, or angle P is congruent to angle P. So if you ever want to say something is the same as itself, which of course it is, everything's the same as itself, the reason for that is the reflexive property. So I said you can use it in proofs like this. If you look at these two triangles, let's say I was trying to prove these two triangles are congruent. And what I notice is that they're like stuck together. They have what we call a shared side. So this side right here, I'll highlight it in red, that's the third side of both triangles. See, what we have is this side is congruent to this side. That's one S. This side is congruent to this side. That's a second S. What I would do if I was finishing the proof is I would say, statement, line segment AC is congruent to line segment AC. I'm basically saying that that red highlighted side is congruent to itself, which of course it is. Everything's congruent to itself. And now that becomes the third S in both triangles, because that is the third side of both triangles. So when you have two triangles that are stuck together like that and they have a shared side, it's like a free S for one of your theorems. The side will always be the same in both triangles. It's always going to be congruent to itself. You just have to say it's congruent to itself, and your reason will be the reflexive property. So for this proof, the first thing, my statement would be AC is congruent to AC. My reason would be reflexive property. And then I would be able to say the triangles are congruent by SSS, because I have all three sides. So that's a very common property to use in a theorem like this. Okay, let's do an actual proof here. So let's take a look at this picture. We have these two triangles that are like sort of point to point. It looks almost like a bow tie. There's some given information, and we're asked to prove that triangle ZYU, which is the one on the left, is congruent to triangle XVU, which is the one on the right. So let's set up a statement and reason, a two-column proof here. Let's do statements and reasons. And with every proof, remember, you get one thing for free. I don't even think about it. The very first thing I do, before I even think about how I'm going to solve this proof, is I take whatever is given and copy it down. So I'm going to say line segment YZ is congruent to line segment VX. Line segment YZ is parallel to line segment VX. And U is the midpoint of VY. Reason given. That's what was given in the question. So that's automatic. I don't even think about that. Now let's mark all of that on our picture. YZ is congruent to XV, so this one is congruent to this one, and that's one of our S's. So we're trying to prove the two triangles are congruent. We have an S so far. Now the second part says that YZ is also parallel to VX. So in addition to being congruent, I'm going to put a parallel marker on it too. And remember, we do that with the little arrows. So if you ever see these two marks together, what it means is those line segments are both congruent and parallel. Now the third part of the given was about a midpoint. I can't mark that, but I can use that. So I think that's going to be my statement number 2. Let's do the part about the midpoint. We know by the definition of midpoint is exactly halfway, so it cuts two things in half, or it cuts one thing in half, cuts something into two congruent pieces. So if I look at it, if Vy is cut in half exactly by U, then what that's telling me is that this piece is congruent to this piece. So let's say that for our next step. That would be line segment YU is congruent to line segment UV. And for the reason, I'm going to say definition of midpoint. Now remember, I've told you guys before, I'm not super picky about wording. You know, basically if you say anything about midpoint, I'm giving you credit for that answer. If you said the midpoint theorem, or if you said just because U is the midpoint, you know, if you say anything about midpoint, if I know that that's the reason you knew that those two pieces were congruent, I gave you credit for it. Okay, so that's my second S. So I have two S's. I have S and an S. At this point, based on the two theorems we've learned, I can either try to show the third side is also congruent and do SSS, but I can't do that based on the given information. It wasn't given that U is the midpoint of ZX. If it was, then I would have SSS. But see, I don't know the third sides are congruent. So let's see if we can prove the angle in between those two S's is congruent, and then it'll be SAS. Now, the one thing I haven't used yet from this problem, from the given information, is the fact that the two lines are parallel. So let's try to use that. Now, the two lines that are parallel, what we did in module 13, we just finished this actually, or module 12, we just finished this actually. We talked about two parallel lines in a transversal. We got angle pairs like alternate interior, alternate exterior, corresponding. Let's see if we can use that. So what I'm going to do, I'm going to take my two parallel lines and kind of extend them. Imagine them if they kept going in the picture. And then I'm going to extend this one too and make this my transversal. Now when you do that, it makes it a little easier to see. Imagine, so the line segment ZX, kind of block that out for now. Because what you actually have, if you look very carefully, this angle right here and this angle right here are what we call alternate interior angles. And we learned that alternate interior angles are congruent. So that's step 3. I'm going to say that, and let me actually clear out some of the lines now to make it easier to see what we're doing. I'm going to say that angle Y is congruent to angle V. And for my reason, I'm going to say alternate interior angle theorem. Alternate interior angle theorem. And I love my abbreviations. ALT for alternate, INT for interior. I use the angle symbol. I use THM for theorem. That's totally fine. Feel free to abbreviate. Again, if you tell me anything about alternate interior angles, I'm going to give you credit for that. Now what we have in order around each triangle is SAS. Side, angle, side in one triangle. Side, angle, side, exactly the same in the other triangle. So I can then say this, what I was trying to prove. I can say triangle ZYU is congruent to triangle XVU, and for my reason it's SAS. I mean, really it's called the side angle side congruence theorem, but just write SAS, that's fine. So some things to think about. Anytime you're ready to actually say that two triangles are congruent, it's going to be one of our letter theorems. It's going to be either SAS or SSS, and we're going to learn two more tomorrow. But the idea is you got to get there. You got to get enough S's and enough A's and the right combination so that you can either say SSS or SAS. And that's the hard part. I think the hard part of this particular one was the alternate interior angle theorem. Was you guys realizing, even though you didn't see it, you had to extend the parallel lines and extend the transversal, and you had to make it so you could really see that those were alternate interior angles. But once you got that extra A, you knew it was an SAS.